Thanks for the introduction. And is the microphone working? Okay. Hello? Yes. So today I'm going to introduce hardware-assisted data flow isolation. This is a joint work with Georgia Tech and Seoul National University. So in this work, our focusing is memory corruption vulnerabilities. And due to the popularity of C and C++ programs, and especially in daily use large programs like kernels, browsers, memory corruption vulnerability is very common. At the same time, memory corruption vulnerability is highly exploitable. They can usually lead to arbitrary memory code execution. So for this reason, they are one of the most widely exploited vulnerability type. And according to the statistic from Microsoft, memory corruption vulnerability is the dominant root cause for remote code execution on Windows. So to understand how memory corruption vulnerabilities can be exploited and prevented, let's use this very simple Stack Overflow example as a running example. As we can see, the program at the left side has a buffer Stack Overflow vulnerability, and the corresponding assembly is on the bottom. So at line 2, we allocate a new buffer, and at line 3, we push the return address on the stack. At line 6, when we call the string copy, if the passing argument is large enough, we can overflow the buffer and compromise the return address. And finally, if attacker can control the return address, they can leverage this to launch a variety of different kinds of attack, including like code injection and return-oriented programming. So there are many defense mechanisms being proposed to defend this kind of attack. For example, the most widely used one is called stack guard or stack cookie, which inserts a canary value between the buffer and the return address. So if overflow happens, this canary will be corrupted, and then attack will be detected. Unfortunately, if attackers can directly write to any given value address, or if there is an information leak vulnerability, this defense mechanism can be easily bypassed. Alternatively, we can also try to encrypt the return address. So even if attacker can compromise this return address, they cannot control the decrypted value. The challenge here is how to do key management. Basically, if we ever reuse the encryption key, then the encryption scheme can be broken and the attacker will win again. Finally, we can also try to relocate the return address to another stack and isolate it using different approaches, including software-based and hardware-based. However, this shadow stack also has many limitations. For software-based shadow stacks, the major limitation now is that in 64-bit world, we lack a good isolation mechanism. Basically, in the segmentation in x86 is gone in 64-bit, and access domain is also gone in 64-bit ARM processors. As a result, for security solutions, we have to choose between efficiency and security. So for solutions that opt for security, such as using masking or a virtual address-based isolation, they are secure, but they are slow. On the other hand, for solutions that opt for efficiency, such as using random-based isolation, they are efficient, but has been proven to be broken. For hardware-based shadow stacks, the problem is flexibility. So existing or proposed hardware-based shadow stack has problems supporting features like set jump, long jump, deep recursion, and sometimes kernel stacks. And because they are specialized to protect only the return address, it's very hard for them to reutilize them to protect other types of data, such as other co-pointers or non-control data. In addition, the data shadowing itself also adds additional overhead. It breaks the data locality, requires additional steps to look up the shadow data, or requires reserved registers. At the same time, there is unavoidable memory overhead. So to overcome these limitations, we propose HDFI. As a hardware-enforced isolation mechanism, HDFI is both secure and efficient. At the same time, we designed to be a generic data isolation mechanism. So it's very flexible, and as shown in our paper, we can utilize it to build different kinds of security model and applications. We also design HDFI to be fine-grained so as to eliminate the need for data shadowing. Finally, to ease the adoption in practice, we try to, during our design, also try to minimize the hardware changes. So HDFI is inspired by the data flow integrity work published in OSI 06. Basically, similar to control flow integrity, data flow integrity enforces that the runtime data flow should not deviate from the model generated from static analysis. To enforce that, DFI first assigns every write instruction ID, and then it extends the memory model to record the ID of last writer. For example, if when we push the return address onto the stack, we will modify the corresponding tag to record the last writer is, say, line 3. And if there is a buffer overflow happens, we will record that all the last writer actually the line 6. Sorry for this. And then at every load instruction, we will check whether the last writer is within the allowed set. For example, in this example, the only allowed write instruction that to write the return address would be line 3. And if overflow happens, we will detect that, and the exception will be generated, and the attack will be prevented. So HDFI includes 2 parts of extensions. First is the ISA extension. So we extended the memory model to include for 1 additional tag for every machine word. However, instead of trying to support arbitrary lengths of tag, we found that in real applications, 1-bit tag is enough. So in our company implementation, we only support 1-bit tag. We also introduced the 3 new instructions to manipulate and check the tag. Store and set 1 will store a value to the memory and automatically set the tag to 1. Load and check 0 will check if the tag is 0, and load and check 1 will check if the tag is 1. So we don't have an explicit load and store and set 0 instruction. Instead, we modified the traditional or original store instruction to implicitly set the tag to 0. And for load instruction, we didn't change any semantic, so we can be backward compatible with existing binaries. So for hardware extensions, our main modification is between the main processor core and the external memory. We extended the cache line to include the additional tag bits so as to support our new instructions and reuse existing cache coherent interconnect. And because we cannot extend tag to main memory, which is DRAM, we also basically store all the tag bits in a big bitmap called tag table, and introduce this memory tagger to duplex memory access to be 1 data access and 1 tag access. However, if we naively implement this, it will introduce too high performance overhead because we doubled the memory access. To reduce the overhead, we introduced 3 optimization techniques. First is we introduced the tag cache in the memory tagger so as to exploit the locality of memory access. The second one is called tag value bit. It's based on the observation that during normal executions, most load instructions will not check the tag. So when we're refueling the cache line, we don't always need to fill up with the value tag. And the last one is called the meta tag table. This is based on the observation that during normal execution, most of the bits in the tag table will actually be 0. So if a line of the tag table is all 0, we will just don't load it from the memory or don't rewrite it back to memory. So having this new feature, let's go back to our Stack Overflow example and see how we can use HDFI to defeat the attack. The implementation is actually quite simple. We just enforce 1 simple policy. That is, the return address should always be have tag 0. And this can be easily enforced by using SD-set1 to store the return address to memory. And when loading it, always use LD-check1. Compared to existing hardware-based shadow stack, our implementation is very simple and it's very flexible, can support all these features like context saving, restoring deep recursion, modify the return address, and the kernel stack. So besides the return address protection, to demonstrate the flexibility of HDFI, we also implemented a variety of other security applications, including vtable protection and code pointer separation, which protects the control data, and standard C library enhancement and data and kernel protection. We protect the integrity of non-control data. We also have one demonstration on how to utilize HDFI to prevent information leaks such as the heartbleed attack. So we implemented HDFI based on the RISC-V Rocky Core generator with about 200 and 2,000 lines of code, and instantiated on the Xenix FPGA board for evaluation. For the software side, we modified the toolchain to recognize our new instructions and handle our new exceptions. And for security applications, the implementation is quite simple. I will talk more later. So for evaluation, we focus on 3 parts. The first part is the effectiveness of our optimizations. As shown in this table, when combining all 3 optimizations, the runtime performance overhead introduced by this new hardware feature is actually negligible. As the second, in second evaluation, we evaluate the security mechanism we built with some synthesized attack we built. And as the result shows, we can defeat all these attacks. Finally, and most importantly, we evaluated how HDFI can change existing security solutions from 4 aspects. First is security. So basically, being a hardware-enforced isolation mechanism, the security guarantee based on HDFI is much better than most pure software-based isolation mechanism. The second one is simplicity. Basically, by eliminating the need for data shadowing, the application built upon HDFI is much simpler. For example, our return address protections application is way simpler than existing shadow stack implementations. And the third one is usability. We evaluated how easy it is to implement a new or existing or port existing security solution to be HDFI based. As shown in the table, the effort is quite minimal. So for example, to implement shadow stack, we only modified the 4 lines of code in LLVM and etc. Finally, also evaluated the efficiency of HDFI-based solutions, and we can see the performance number is quite good. The only exception is for CLAM-based solutions because of the immaturity of the current toolchain. We can only compile with 0. And being in-order execution core, we are quite sensitive. Our current implementation is very sensitive to compiler optimizations. That'd be all, and any questions?
Any questions?
Talk. Can you hear me?
Yes.
Thank you. I agree this would work really great for x86, but in a more modern instruction set like ARM, many return addresses never find their way to memory. They sit in the link registers. Can you protect those as well?
Oh, yes. I think our current implementation actually based on RISC-based architecture. So as probably you didn't notice, but actually in the example we showed, the Stack Overflow, we're using the stack is stored into the memory using SD link register to the stack. So actually we can, our current implementation actually is more like ARM and RISC-based instead of using using call and return.
Maybe I didn't express myself very well. So
Yes.
A leaf function on an instruction set with a link register never stores the return address.
No, but once you have link register is when you call, you put the return address into the link register. But if you have if you're not the tail call, if you're not the last call, right? If you have to call again, right? The link register then will be modified. So before that call, you still have to push link register onto stack.
The reality of dynamic execution is everything's in a leaf function. That's where the dynamic vulnerabilities are.
I think I couldn't agree with that. Based on my experience and all the programs I compiled or tested, they always save link registers to the stack if they call additional functions.
But most of the time is in the leaf functions. Otherwise, you'd be calling functions more than you would be executing instructions.
Yes.
But we'll take it offline.
Yeah, sure.
Thank you.
On this side, please, on the other side. Quick question.
Yes.
So where does your overhead come from? I wasn't quite sure where you're generating all this performance overhead.
So the performance overhead is compared to the unmodified hardware. So because in this new hardware, we need to fetch, for example, especially we need to fetch the additional tag bit from the tag table. So that's the main overhead, where the main overhead comes from. Because we cannot have in the DRAM to be tagged. So for every memory access, we have to duplicate the access. Right. So this is the main source of overhead.
Thank you.
Yes. Yes.
So on your slides, you gave a number of different uses that this extra TIG bit can be used for.
Yes.
Are those uses actually compatible with each other? And if not, then how do you deal with the fact that one in compile might use the TIG bit for one purpose, and then some other bit of code is compiled separately and uses it for a separate use?
So basically, they are. I think they are compatible. Basically, the thing is we use HDFI to tag sensitive data, and all sensitive data will have different meanings. For example, return address will never overlap with, for example, vtable pointers or function pointers, or return address will never overlap with, say, UID in the kernel. So in that way, if you look at the memory, you will say, okay, all the sensitive data, they will be disjoint. And so all these applications can be combined together to, they will not affect each other.
Well, I mean, couldn't a return address be
Yes.
overwritten by some code that it thinks it's writing a crypto key or something like that, which you also consider sensitive?
Yes, so I think if you are mentioning that, I think I have sorry. Could you go to one slide more, or maybe? So I actually have a backup slide talking about this. So all this is based on DFI. So the thing is we have to rely on the data flow analysis. So basically we need to be able to control where the pointer points to. So so therefore to defeat, I think to handle the case you are mentioning to, we probably need additional runtime memory safety enforcement to make sure that, okay, you have this instruction and you want to write it to a target, we need to make sure that the target you want to write to. Does this answer your question? So for example, you have a constructor, attacker may try to use this constructor to overwrite the return address by overwriting return address with a vtable pointer. But in that case, we probably will need additional runtime memory safety mechanism to prevent such cases. And actually, our original goal for HDFI is to be assisting memory safety mechanisms such as MPX to achieve selective protection. So we only need to isolate some more important sensitive data and apply memory safety only to those kind of data.
Okay. And I also noticed that on your performance overhead chart,
Yes.
there seemed to be one performance overhead which was negative.
Oh, I think it's for spec, there's natural fluctuations. So like 1% is within the standard deviation. So it's basically, I don't think it's quite meaningful.
Okay.
It's just the result of one test case. Yeah.